And now we're into reflection. You did reflections last year. The reflections that you did last year would have been a reflection in the x-axis. So it was, remember when you had a quadratic and it had a negative leading coefficient instead of it being concave up, it's concave down. It's actually a reflection in the x-axis. Okay? So we're not going to just do reflections in the x-axis, we're actually going to do reflections in the y-axis as well. All right. So reflections in the mirror image go along their axis. Invariant points, the points that do not move after transformations. And we talked about this last year. Invariant points, that's not meant to be crossed out, that's meant to be underlined. So invariant points are the points that do not move after transformation. So some people follow that on an original graph there was a point, say here, right? And then the new graph moves, and this point here actually goes on top of this point, just like sheer luck of transformation, right? People will say that's an invariant point. Well, it's still there. That wasn't the original point that's still there, right? So an invariant point has to be the point and it did not move. Okay? So an example, a quick example of an invariant point would be, okay, if I give you this graph. I gave you that graph. Notice you draw it, and I asked you for the invariant points when this graph is reflected on the y-axis. Okay, so the y-axis would be here. This will make more sense. Okay. This will make more sense later, right? That's our mirror, our y-axis. Okay, it's reflecting on that. So what happens is you're going to get this arrow down here, and this squiggle, if I get my circle one off, better. But you literally just get a mirror image of it along the y-axis, right? So where would the invariant points occur on this graph? Yeah. Every time this graph what? Is on the what? Is on the y-axis. So your invariant points occur on the reflecting axis. So this axis flips, but this point isn't going to flip. It was on the y-axis. It's staying on the y-axis because that's the mirror. It's just like if you put something, if you went into your bathroom and you put something against the mirror, say, right? What's the part that doesn't really change? The part's against the mirror, correct? That would be your reflecting axis. Same thing here. This is your mirror. It's not going to change. It's on it. So your invariant points occur in reflection, wherever the heck you're reflecting on. You're reflecting on the y-axis, so it's going to be where your invariant points are. You're reflecting the x-axis, that's going to be where your invariant points are. If you reflect, which we'll do later, on the inverse line, which is the line y equals x, which we did last year. You didn't reflect on it, but you did look at inverse. Then that's where the invariant points are. Because wherever the mirror is where the points are, right? You don't flip or change, because that's where you're flipping on. So let's look at this one. Reflection in the x-axis. So this is what you did last year. Okay. Not like the rest are fantastic. Okay. That's what I was thinking. Okay. So we have the negative f of x in front. So when the negative is in front of the x, what could you do? Where could you move that? You could move it with the y, correct? We could do this. I'm just saying negative y equals f of x. When it's with the y, it's a reflection of the x. When it's with the x, it's a reflection of the y. It's the opposite. Reflection of the opposite. So, the graph of y equals f of x, x squared minus 4x plus 4 is shown. No, it's a lie. It's not. We're going to show it. So, x squared minus 4x plus 4. If you want, we're going to subtract with my calculator. So, you go to y equals and type x squared minus 4x plus 4. We're going to take that 2 and 0. You're going to have your calculator. And then we need a few more coordinates on both sides of 2 and 0. Where's the quick way to find those in your calculator? Second, graph. What's the word behind graph? grade 10 when they used to make you come up with the table of values so you can graph the graph from grade 9 you can do. You're calculating those for you. One second, graph. Now you want to look for 2, 0. You want to take a couple points on the left of it if they fit on the graph. And a couple points on the right of it so that you get the symmetrical graph, right? You get the full graph, not just pieces of it. So 2 zeros are already vertex, the minimum of it. And then I have on the left of it, I have 1, 1. And I have 0, 4. And on the right of it, I have 3, 1 and 4, 4. Smartboard off. Okay. So we have our graph. Now, what does the equation y equals negative f of x mean? It means that I'm taking, this is like saying negative 1 f of x. It's essentially like saying negative 1 f of x. What is f of x? F of x is x squared minus 4x plus 4. So we're actually trying to go y equals negative f of x. F of x is all that. X squared minus 4x plus 4. So what do you actually get? Y equals negative x squared plus 4x minus 4. Put that into your y2. Put that into your y2. Now there's some of you that don't know this. So into your y2, you're going to put in negative. You have to put it in the way you say it. So if you go subtraction x squared plus 4x minus 4, if you do that, you're going to have to get the same graph. You want to type it in the way you say it. This is negative, so you have to use the negative button. That's why you enter. X squared plus 4x minus sine 4. You have to put it in the way you say it. So negative x squared plus 4x minus 4. Now, for all of you who were in my class last year, I don't know if the teacher taught this or not, but I like it this way so that I can actually see. So I have two graphs. When you press, don't press graph, but when you press graph, it'll draw the first graph first and the second graph second, correct? Now, when it does that, unless you have the fancy those different colors, when it does that, that's great. You know what's first and second. Then you put your calculator down, you start working on the question, you go back and you're like, oh no, which one's which? These are more obvious because one is a positive leading coefficient, one is negative, so you know which one's which. But when they're both like positive and they're just kind of like this, and then you start doing your work, and then you come back and like, which one is the right equation? Okay? What you want to do is you arrow all the way, so you're on your second equation, and you arrow all the way to the left, so you get to this. Y2 equals negative x squared plus 4x minus 4. You want to be blinking on this. You want to be blinking on the slash. Hit enter. Once. Only once. What happens to the slash? It got bigger. Now press graph. Now you know the thicker one is actually y2. Okay? This is a little obvious because, like I said, one is concave up, one is concave down. But when they're both like just transformation of each other or stretch, it's just better, it's easier. I like this. Now, does it look like it actually reflected in the x-axis? If I put a mirror straight on the x-axis, so now we have this. So if it reflects on the x-axis, it's there, and we have here, and then this is at 4, so we get negative 4, negative 4. Your graph like this. Correct? So it's a reflection in the x-axis. If this is my mirror, and I have a mirror, and up here now, it's going to reflect down. Correct? So it's a reflection in the x-axis, which is true. But what changed on the coordinates? Did the x value change? No. Did the y value change? Yes, they became the opposite sign. So if I had started out with this original graph, and the black is being the original, then the red would be a reflection in the x-axis. What happens when you have a reflection in the x-axis is you have a negative in front of your y, correct? You have a negative in front of your y. All your y's are multiplied by -1. So if you did a mapping, your original equation, the original point would be xy Your new points are going to be x, comma, negative y. Your x side is all still the same, but your y is 8. That could be just a reflection. Do you see how we're going to put them all together in like 2 lessons? They're going to be put all together, your instructions, reflections, and translations. You need to know your basics really, really well, so when you put them all together, you're not like fully like that. Okay? What are the coordinates of the invariant point? Which point didn't change? The one on the x-axis. So 2, 0 is my only invariant point. And remember, I told you that when it's a reflection in the x-axis, wherever you reflect on, your invariant points are the ones that are on that axis. So, I'm seeing too hard. This one is one you can type right in your calculator. Not that nice usually. Sometimes they'll give you a graph like this. That's so crazy. Pretend. Okay. And they call this f of x. Okay, that's f of x. And they tell you how many invariant points are on the graph of y equals negative f of x. And you're like, what's the equation? Like, can I do my calculator? And I can tell you how many types of fractions. You're like, oh, 2. They don't give me the equation. And then decide, or do scale. You don't want me to do that. I don't want scares with dehydration. So, remember that negatives can be divided over, so you actually have a negative y. So when you have a negative y, what does that mean? You have a reflection in the x. So the opposite. So you have a reflection in the x-axis. If you have a reflection in the x-axis or a reflection at all, where are your invariant points? On the line you reflect on, right? So how many invariant points are there here? 1, 2, 3, 4, 5. I've seen questions like this on the phone before. They'll give you a graph, and they'll give you the transformation, they'll tell you it, they'll give you an equation, and they'll say how many invariant points are there. And then it's like 3, 2. Count. Reflection. Okay. How does the graph of y equals negative f of x compare to y equals f of x? Well, this can be negative y equals f of x as well, remember? It's just a reflection in the x-axis. So instead of y, it's reflection in the x, and with the x, it's reflection of the y. So here's what I was saying. The graph of y equals f of x is shown. Sketch the graph of y equals negative f of x. So negative y equals f of x. What happens when you have a negative y? You change all your y's to negative y. So if they were a positive y, they're going to become a negative y. And if they're a negative y, they're going to become a positive y. Hence why they reflect on the x-axis, right? Anything up here is going to go down here. Anything down here is going to go up here. What happens to those x values of the coordinates? Anything? No, the x values stay the same. The y is just y. So here's my reflection line. These are going to stay because they are on the x-axis, and they're my invariant points, and they don't change. Then, this one is at, you don't see every single point either. This is like kind of in the middle somewhere at. But this one is at negative 1 and 1, 2, 3, 4. So what's it going to be at? Negative 1 and negative. So the now thing is my x, y coordinate is going to become x and negative y. My x nothing's going to happen. Then I can take this point, it's going to go here. Same thing, x, y, and right here. Here. So we have the processes right out. And you might be like, so your arrows go further left. Arrows can go further. Hey, now we have a reflection in the y-axis, so the negative is going to be with x. So, x and we can't move it, it's just in front of the x, right? Like the y one we can move, just like we can move the vertical translation, right? We can move the reflection with the y as well. The x is with the x all the time. So what does that mean? You guys, you did function notation in grade 10. You did a bit of it in grade 11. What the heck does this mean? When you have f of something in the bracket, f of negative x. If I gave you, let's go back to 10. If I gave you x squared plus 3x, and I told you that was f of x, and I told you to tell me what is f of 2, what would you have done? You put 2 in front of x, right? Whenever I insert something into this bracket, that means that's what x represents, right? So you would have said 2 squared plus 3x, 3 plus 2, sorry, which is 10. Okay, that's what you would tell me. Sometimes in grade 10 we go, okay, what's f of b? We say, okay, well then I just go b it. So I go b squared plus 3b. And that's all, right? So for this one, I have f of negative x. So what am I going to do? Replace all my x's with negative x. So I'm going to go y equals x squared here. So I'm going to go negative x squared minus 4 times negative x plus 4. What happens when I square negative x? As a positive. I'm going to get x squared plus 4x plus 4. So let's graph the first one on there, and then we're going to graph the second. The second one you'll have to type in your calculator. So the first one is the original one we had last time. So 2 0 1 1 3 1 0 4. So it's the same equation that we started with last. But now we're reflecting in the y. So, all my points, what's going to happen to them? They're going to flip over, right? So if they go from here to over here, from here to over here, what's changing the y? So my x's are being negated. So if they were over here, they'd be negative, and then they'd be positive. Over here, it's positive, negative. And my y's are going to stay the same. So if I get mapping, it seems like x, y are going to become negative x, y. The y helps stay the same. And the x gets moved, just like it says. So the only invariant point is going to be this one, because it's on the reflection. This is going to be over here. This is going to be over here. This is 1, 2, 3, 4. This is 1, 2, 3, 4. The coordinate of the invariant point is going to be at 1, 2, 3, 4. 0 and 4. Why is that? Well, think about this. Why is that? I told you I multiply all my x's by negatives, right? So if my point was at 1 to 4, let's say, it's going to be at negative 1 to 4. Yeah? So why does 0, 4 say 0, 4? So that's what I'm saying. It's invariant. 0, 4 says 0, 4. Why? When you multiply 0 by negative 1, what is it? 0. So the other catch is, if your x is 0 and you're reflecting in the y-axis, remember that point is the same. If it was a 4, 0 and you were reflecting in the x-axis, that's going to stay because you're going to multiply all your y's by negative 1, right? You multiply the 0. How does the graph compare? It's a reflection in the y. The graph of this is shown. Please do f of negative x. Okay. So it's a reflection in the y. So this point stays. This point coming over here. This point coming over here. This point over here. And here. This one. And here. I'm going to go like that. Okay? This is what. Always generally you have more than one color at this point. So, you have a pencil or pen, or if someone beside you, you have a pen and pencil too, or you have a highlighter, or I don't know, lots of highlighters. Highlighters just look very on here, I want you to stretch. This one is a reflection in the what? In the x-axis, because it's not with the x. This one's with the x, so it's a reflection in the y. The only way you get a reflection in the y-axis is if your x's become negative. The only way you get a reflection in the x-axis is if the y. So I want you to try and draw those two fractions. Okay, now I'm going to do the green one for the reflection of the x-axis. And these are going to stay. Now, you guys, please pay attention. Everyone does this ground on the test. Okay? I'm going to erase it. So I give you a graph like this, and I say to you, how many invariant points are there for the reflection of the x-axis? You know, many of you will tell me there's two. This one here and this one here. Because they're legit points that go through a cross section. But how many are there actually? There's 3. You have to look at the whole reflection. This one is reflected, this one, and this one. I promise you, a whole bunch of you will pick 2 because these are like legitimate points that are bolded. And you'll forget about this one because you're like, oh, but it is actually coordinate that goes through there. Whenever I get a question like that, I lose like at least half of you. Okay? And then when you get to the test and check your corrections, you're like, oh, stupid, everything. So we don't want those. So make sure you draw the whole reflection line if you really want to, so that you know how many times you're crossing. That works as well. Okay, now these are at 1, 2, 3, 4, 5, 6, and this one is 2. This is 1, 2, 3 out. This is 1, 2, 3. And then next. Then this one is the reflection in the y. So anything on the y-axis stays. This is going to move over here. So negative x is positive x and positive x is negative x. What I would have you to do as well is move from like the left side of the graph to the right side of the graph, or you can't remember which graph point you move, which is what I said. So, I start here, go here, then do this one, then do this one, that one, and this one. All right. The graph drawn in the thick line is a reflection of the graph drawn in the thin line. So the thin line is the original, the thick is reflected. Write two equations for each function. So we'll pretend that this is f of x, and then this one is yes. We need a new equation. You can say things, but remember, your invariant points happen on the reflection spot, right? So the first graph, where's the invariant point? On the x-axis. So on the x-axis, that means the reflection in the x-axis. Those invariant points happen on the y-axis, so they're a reflection in the y-axis. So this is reflection in the x-axis. That means with the y, you're going to have a negative f of x, which I could also write it as or y equals negative f of x. So I could divide by negative 1. This one is a reflection in the y-axis, so it means I have a negative x, right? So it's going to be y equals g of negative x. And it's only g because I took the original equation. Okay, doesn't matter what the function looks like, it doesn't matter if it's 10 to the x, you have no idea what the heck that looks like, it's an exponential function. Just matters where the y and x are. When there's a reflection in the y-axis, what becomes negative? The y on the equation or the x? When it's a reflection in the y-axis. You get a negative x on the equation or a negative y? So it's the opposite. You get negative x. So I'm going to get a negative x. So when I go to rewrite this equation, I'm going to get y equals 10 to the negative x. Now, whenever they give you an equation, you can always punch the one into your y equals, punch the other one into your y2, and see if they actually do reflect where it says. You check yourself. If they give you the equation. Try B. If it's a reflection in the x, that means your y is negative. So we get negative y equals root x, which means we could divide by negative 1 both sides. So we have y equals negative root x. Either of those. Okay, when we get an equation, what do we do? So this is y equals 6x squared plus 3. So this negative that's in front here could be with the y, correct? So that's how I always start it. So I'm going to do this equation. Y equals 6. I find everyone does an equation better when they start the y when it's negative with the y. Then if they leave it here, then they're like, oh no, they're going to go the whole thing, part thing, right? So this negative here could actually be written in front of y, right? They mean the same thing. Well, I want to be able to graph it. In order to graph it, so you put in my calculator to look at it, I have to have a y. So I'm going to divide by negative 1. If I divide this whole side by negative 1, I'm going to get y equals negative 6x squared. Remember, when you multiply by a negative 1, it's just negative 1 over 1, is it not? We multiply by anything that's just a digit, negative 1, that's what this is. You can never do 1, that's what you do with every number, correct? So this can just be written as negative 6 over x squared plus 4. The only catch is if you have a binomial in the numerator or denominator, binomial meaning 2 terms, or trinomial 3 terms, or whatever. If you have more than a monomial, and you want to punch in your calculator, you have to put in brackets. You can't just go negative 6 divided by x squared plus 3, because what your calculator thinks you're doing is negative 6 divided by x squared plus 3, which is what you're actually asking to do. So you have to remember to do this. So punch that into your y equals. Punch in the original one, punch in the new one. What you're going to notice is your original is here, and then it's doing this. That's not normal at all, but imagine this. So you're going to get this, and it's going to reflect on the other. Because like you learned last year, you have an asymptote here. Where the graph has right on the set. And if we do this function here, we're replacing our x's with negative x. So we're going to get y equals 6 negative x squared plus 3, which is y equals 6 x squared plus 3. What happens? The entire graph is invariant. Why? It's the exact same. How could it be the exact same? Now this graph is was drawn properly, which is but the red graph is the original graph. It's symmetrical above the y-axis. It's symmetrical above the y-axis. So if I actually flip this way, or flip this way, it's the boundary chart, right? So people would tell me the whole graph is invariant. Is the whole graph invariant? Or is there still only one invariant point? The whole graph looks invariant, but remember what's our rule about invariant points? They can't change from the original. If I flip this red graph, then this part of the red graph will go over here. So they actually did change. All these points are over here now. And all these points are over here. So still only have one invariant point. The graph looks invariant though, because it flips over itself, right? But it's not. Try example 9 and 10. So we have this negative here. It's in front, so we can write it with the y. Negative y equals square root x minus c. You can write it that way. Or you can move it over. And write the negative in front. Yes. You didn't put the negative x in. Minus c, so you put the negative x. All right. All right. Y equals x squared plus 1 is the equation of a reflection in the y-axis. So if it's a reflection in the y, I get a negative x, correct? If the y equals negative x squared plus 1. We have to get the exact same graph. Why did you get the exact same graph? Remember the graph. The graph is actually symmetrical above the y-axis. Okay, so that graph has a vertex at 0 and 1, so it's up a little bit, 0 and 1, and it's symmetrical above the y-axis. So if I reflect it in the y-axis, it's just going to look the same, right? That's why that would be the case. And then this equation is reflecting the x-axis, so I get a negative y. I'm going to get negative y equals x squared plus 1. Now, I want to see how many of you got this correct. A whole bunch of people will write y equals negative x squared plus 1. You know that you are not correct. Remember I said to you, you always have to put any type of transformation that is on a graph that has already been transformed. This graph is already transformed, right? That's on the graph. It's not just y equals x squared, it's a transformed graph. If you don't remember to put it with the y and then move it over correctly, you will get it wrong and you will have the wrong answer. If I divide by -1 to move it over, I'm dividing the whole thing by -1. So I would actually have y equals -x squared minus 1. And if you're lucky enough to be given the equation, please punch in the original and punch in the one you think you're correct with and see if it actually reflects what it's supposed to. That's the exception. However, if they don't give you the equation, you can't do that. So it's a little estimate.